let's consider the motion of an object moving along the x-axis. That is, the object is restricted to moving only in one dimension. I have a diagram that is showing the motion of this object here. And the object is going to start at position x1 at a time t1. And it's going to move to the right through positions x2, x3, and x4, turn around and reach position x5, and eventually come to position x6 at a time t6. The red line that I've drawn represents the distance traveled by the object. Distance is an important word in physics, and what you need to know about distance is that distance represents the length of the path that was traveled by the object. So let's write that distance is the length of the path. And so if the object travels a greater distance, it's traveling along a greater path. And distance is something that can be measured in centimeters and meters and miles and kilometers, and it will have a physical size to it. It can be 0 or it can be positive, but it can't be negative. And that's because there's no direction associated with distance. It's just a measurement of the length of a path. And so when a quantity has a magnitude, it has a size, but it has no direction associated with it, we call that a scalar. And so distance is a scalar, which is a measurement of the length of the path traveled by an object. A quantity that is like distance but not quite the same is something called displacement. And displacement is a very important quantity in physics, and it's not the same thing as distance, and the difference is displacement is defined as the distance from an initial position, which we'll call xi, to a final position, which we'll call xf. So displacement is related to the distance between two positions, xi and xf. But displacement gives us two pieces of information. It not only tells us the distance between xi and xf, but it also tells us about the direction. So the direction from its starting position to the final position. And for that reason, displacement is a vector. So displacement tells us not only the distance, but also the direction. And if I was going to let the initial position in this diagram that I have up above be x1, and I let the final position be position x6, then the displacement vector between those two positions would start at xi, and it would point toward xf. And so vectors can be represented with arrows. And here this arrow represents the displacement vector from position x1 to x6. And displacement is a quantity that we will typically use the symbol delta x for. So displacement is often symbolized by delta x, and distance is often symbolized by just a letter d. And so distance and displacement can be different. And here in particular we see that because the distance was represented by the length of that entire red line, whereas displacement was just a distance that starts at x1 and goes to x6, which is much smaller, but also has a direction associated with it. When we are doing motion problems in physics, it's important that when we have an axis like this, here we have the x-axis, that we define which direction is the positive direction and which direction is the negative direction. And so here I'd like to select the positive x direction to be to the right. And if I let the positive x direction be to the right, then one way we could describe the displacement of this object from x1 to x6 is that the displacement is positive. Delta x is positive because it points in the positive x direction. Displacement as an equation can be written in this way. delta x, which is a vector, so I'll write an arrow above the x, is the final position minus the initial position. And this should match up to the diagram and what I've said about the direction quite well. I know that the final position xf is greater than the initial position xi because it's further to the right along my x-axis. Therefore, if xf minus xi gives me the displacement, then I should expect the displacement to be a positive number. And that matches up with what I said earlier. That arrow, that green arrow that I've shown in my diagram, points to the right in the positive x direction, and the displacement is a positive number. Now, I don't know what those numbers are, but if I knew what they are, I could plug them in and figure out exactly what that positive displacement is between positions x1 and x6. It will also become important that we be able to describe not only where the object is or how far it's traveled, but how quickly it's traveling. And so there are a couple of quantities that we use to describe how quickly an object is traveling. One of those is called average speed. And average speed is probably the quantity that we're most familiar with. In order to determine the average speed, we would take the total distance that was traveled, and we would divide by the amount of time that it took to travel that distance. And so if I knew the length of that red line, which would be the distance traveled by the object, and I knew the amount of time between t1 and t6, I could use those two pieces of information to calculate the average speed between those two times. A quantity that is different than the average speed, or at least can be different from the average speed, is something called the average velocity. The average velocity. And velocity is different than speed in that distance is not used to calculate the velocity, the displacement is. So displacement divided by the amount of time that was taken to move through that displacement. The amount of time between the initial and final positions would give us the average velocity. And the way that we would typically express that in the form of an equation would not be using all of the words. It would be by writing v, which is a vector, the velocity, and this is an average velocity, is given by the displacement, delta x, divided by the time interval over which it moved from the initial position to the final position. So sometimes we even write xf minus xi divided by tf minus ti. So displacement and velocity really do depend on the initial and final positions, whereas quantities like distance and average speed depend on the total length of the path and the total amount of time. Lastly, I'd like to point out that distance and speed are both scalars, and they can either be 0 or positive, but they can't be negative. But displacement and velocity can be positive, negative, or 0 because there's a direction associated with those quantities, and so if they're pointing to the left, maybe that's in the negative direction, and so the displacement or the velocity can easily be negative. There are many ways that we can look at the motion of an object, and another way that we commonly do that is by looking at position versus time graphs for an object. So this is representing the same object that we were just talking about, whose motion went through positions x1 at time t1 to position x6 at a time t6. And we knew where the object was at different times and different positions, but we don't know anything about what happens in between that until we look at something like a position versus time graph. And so by filling in this position versus time graph, I can give you a picture of what the object is doing in between these positions, which we might not get a sense of unless we look at the position versus time graph. And so maybe the object's position as a function of time looks something like the graph that I've drawn. Now what I'd like to do is select 2 points, and the 2 points I'm going to select are at times 3 and 4. So I'm going to connect those 2 points with a straight line. And if I use that line to create a right triangle, then maybe you can see that the horizontal bottom leg of this triangle is an amount of time, delta t, and the vertical leg of this triangle is a change in position, delta x. And we know that the slope of that hypotenuse, that line connecting points 3 and 4, the slope of that line would be equal to the rise, the amount of vertical rise between those 2 points, divided by the run, the amount of horizontal run between those 2 points. And in this case, because we're looking at a graph of position versus time, the rise is represented by delta x, and the run is represented by delta t. And so since I was looking in particular at times t3 and t4 in positions x3 and x4, then the slope of that line connecting those 2 points would be x4 minus x3 divided by t4 minus t3. And so if this were a actual graph of the position versus time with all of the numbers, you could look at the 2 points 3 and 4 and find those positions and times and then calculate the slope of that line that I've drawn. And the reason why the slope of that line is so important, and maybe you've already seen this, right? It is telling us the change in position over the change in time, which we just saw was the average velocity of this object. And so the hypotenuse of this line represents the average velocity between those 2 points. It's important that we understand and appreciate why we call what we've been talking about so far the average velocity. If we look at the graph, and I look at the line that I connected between points 3 and 4, the line that I used to calculate the average velocity, I notice that those 2 points are far apart. Points 3 and point 4 are far apart. And I also notice that the yellow line, which represented the slope, which I used to calculate the average velocity, is not matching up perfectly with the red line behind it. In fact, the red line seems to deviate quite a bit from that yellow line, which means that the yellow line is not a perfect description of the motion that the object was actually having in that time interval. And so the way that we deal with this in physics is we can take those 2 points, and instead of them being so far apart, we can pull them closer into one another. And when they're closer to each other, the line that connects those 2 points will be a better description, in fact a near perfect description of what the object was actually doing. And so let's imagine this a little bit more visually, right? So here's point 3 and here's point 4, and right now they're separated by some distance. And if I take this point at the top and I move it a little bit further down, maybe to right about here, then the line connecting those 2 points now would be a line that looks something like this. And now you can see that that white line does a much better job of matching the red line that's behind it. And also what I'd like to point out is if we can measure an angle that goes from the horizontal, which would be like this green line that I'm drawing here, up to the line that I'm using to measure the velocity, the yellow line, which I initially drew, had a certain angle there, and maybe we can call that angle theta. And as I move point 4 down toward point 3 and they became closer to one another, that angle of theta changes, right? Now it goes all the way up to that white line. And if I move them even closer to one another, maybe you can imagine that that angle would change by even more. And that angle, in addition to just looking at the slope, that angle in particular can tell us about the velocity. The bigger that angle is, the more positive it becomes, the greater the velocity will be in the positive direction. And if that angle were to dip down below the horizontal, then it would be a negative velocity. Then of course if the angle is 0, the velocity would also be 0. But anyway, as I move those 2 points closer and closer to one another, the velocity that I would calculate by measuring the slope of that line is changing by a little bit. And we use calculus to help us here, and we say that in the limit that delta t approaches 0. So as delta t gets very small, as those 2 points become very close to one another, of delta x over delta t, the limit as delta t approaches 0 of delta x over delta t is exactly equal to a quantity that is not the average velocity, but the instantaneous velocity. And when we refer to velocity in general in physics, we're referring to the instantaneous velocity, which we'll just symbolize with the letter v. And it's still a vector, so we'll put an arrow over it. And you undoubtedly recognize this as the first derivative of position, the first time derivative of position, which can be represented as dx over dt. And so the velocity of an object, v, is given by the first time derivative of position, dx dt. The instantaneous velocity in physics is super important because I can find the velocity at any particular moment in time by finding the derivative of the position function. So if I know of a function that describes the position as a function of time, I can take the derivative of that function to find the velocity. Graphically, I can look at a graph of the position as a function of time and look at the slope of that graph in order to determine what the velocity is. So for example, before we move on, I'd like to just make sure that we know that as I look at the position as a function of time, if I draw a line that is tangent to this graph at any moment in time, a line that only touches the curve at one point, then the slope of that line should tell me about the instantaneous velocity. And so the slope here is positive, and so I know that the velocity is positive. The slope here is negative, and so I know that the velocity is negative. And at the top, at time t4, the slope there is horizontal, and so the slope is 0, and so the velocity would also be 0. And that makes some sense to me because in this graph, before time t4, the object is moving up toward position x4, and after time t4, it's moving back down towards position x5. And so there's a moment in time at t4 there where it changes direction. And if an object is going to change direction, then it has to stop in order to turn around and go the other way. And so t4 is where it stops, and I see that because the slope becomes horizontal. And so please remember that velocity is the first derivative of position, and then I can find the velocity, the instantaneous velocity, by looking at the slope of a position versus time graph. The last quantity that I'd like to define is average acceleration. In the same sense that average velocity was an important quantity because it described to us the rate at which position changes, average acceleration is a quantity that is going to describe to us the rate at which velocity changes. So let's think of average acceleration as the time rate of change in velocity. The time rate of change in velocity between 2 points, and those 2 points are going to be, the velocity and time at an initial position and the velocity and time at some final position. So the average acceleration, A average, which is a vector, would be a quantity that could be expressed as delta V over delta T, or VF minus VI over TF minus TI. And we can follow a very similar line of thinking to go from average acceleration to instantaneous acceleration as what we did for the average and instantaneous velocities. And so you should already know that the acceleration, the instantaneous acceleration, is going to be the limit as delta t approaches 0 of delta v over delta t, which means that instantaneous acceleration, the acceleration is going to be the derivative, the time derivative of velocity. So acceleration is dv dt. If you know an equation for the velocity as a function of time, and you take the derivative of that function, that new function that you get will be an expression for the acceleration as a function of time. And hopefully now you can start to see some of the links between position and velocity and acceleration. For example, if a is equal to dv dt, and v can be written as dx dt, then I could write this as follows. I could pull out the v and instead write it as dx dt. Right? d dt of dx dt would be the second derivative of position or the first derivative of velocity. Either way, those are both expressions for the acceleration. So acceleration is not only the first derivative of the velocity, but it's the second derivative of a position function, which can be written as shown. And so in order to remember all of the relationships among position, velocity, and acceleration, just remember that the derivative of position is velocity, the derivative of velocity is acceleration, and all three of those quantities are linked very closely to one another. When we measure these quantities, positions are almost always measured in meters. Velocities are almost always measured in meters per second. And accelerations, which are measurements that are changes in velocity as a function of time, are measured in meters per second, right? Velocity divided by time. And so we express that as meters per second squared. These quantities are all related, and you should be thinking of velocity as being a rate of change in position and acceleration as being a rate of change in velocity. The last thing I'd like to do before we move on to an example is to just look at a couple of quick graphs to make sure that we understand what's going on with this position, velocity, and acceleration stuff. So the first graph I'm going to draw is a position versus time graph. And this position versus time graph is just going to be a quick sketch, and we're going to look at three different points. I'm going to label point A, point B, and point C. And what I'd like to point out about these 3 points is, we'll start with point A, is that at point A, if I draw a line tangent to the graph at point A, it only touches at one point, point A, then that line has a certain slope and it is directed up and to the right. And so the slope of this line is positive. And if the slope of that line is positive, then that means the velocity must be greater than 0. The velocity must also be positive. If the velocity is positive, that means the displacement is positive, which means the object is moving in the positive direction. Moving on to point B, here the line tangent to the curve is flat. It's 0. And if that's the case, then that means the velocity must also be 0 because this is a position versus time graph. If the velocity is 0, then that means the object is at rest. It's not moving. Lastly, if I draw a tangent line at point C, then I notice that the line is sloped downwards. It's moving down and to the right. And so the slope is negative, so the velocity must also be negative. That means that the velocity is less than 0, and the velocity points in the same direction as the displacement, so this means the object is moving in the negative direction. So that's a position versus time graph. Another type of graph that's very important to us is a velocity versus time graph. So now we need to adjust our frame of thinking a little bit, because this is no longer a position versus time graph. This is a graph that is not going to show us any spatial representation of what the object is doing. It's showing us the velocity as a function of time. So I'm going to draw a similar curve, and I'm going to identify 3 points, and now I'm going to call those points D, E, and F. And let's look at the slope of this line. In the same sense that for a position versus time graph, the slope tells us about the velocity. For a velocity versus time graph, the slope represents the acceleration. And a similar analysis could be looked at. You could make a right triangle in the same sense that I made for the position versus time graph, except you would see for the velocity versus time graph that the vertical leg of that triangle would be a delta v instead of a delta x, and you would find that the slope of this graph will represent the acceleration. So at point D, I notice that the line is sloping upwards and to the right, and since the slope is positive, the acceleration must also be positive. Since the velocity is also positive, right, and I know the velocity is positive because here we are in the first quadrant of this graph, so the velocity is positive and the slope is positive, that means the velocity and the acceleration are both positive. They're both pointing in the same direction, which means not only the velocity, but the change in the velocity is in the positive direction. And that means the velocity is increasing in the positive x direction. At point E, the slope is once again flat. The slope is 0. And if the slope of a velocity versus time graph is 0, then that means the acceleration is 0. If the acceleration is 0, that does not mean that the object is at rest. What it means is that the object is moving at a constant velocity. So the object can be at rest if the graph looked a little bit different than this. But here, the velocity is not 0. The velocity is some positive number here on the axis. And so the velocity is not 0. When that slope flatlines, it just means that the object is moving at a constant speed. Lastly, at point F, I see that the line is sloping downwards like this. But I want to point out to you that the velocity is still positive. If I followed point F over to the left-hand part of the graph, the velocity is still positive. We're still in the first quadrant of the graph. And for that reason, if the velocity is positive but the slope is downwards, the velocity is pointing in the positive direction, but the acceleration is pointing in the negative direction because the slope is negative. Right, on the left it was positive. And so the velocity and the acceleration point in opposite directions. Anytime that happens, the object is going to be slowing down. Its speed is going to be decreasing. And so here the velocity is decreasing in the positive x direction, right? Because the object is still moving in the positive x direction, but it's slowing down. And so hopefully this gives us a better sense of how we can use position versus time and velocity versus time graphs to get information about the motion of an object. The last thing I'd like to do is to look at an example. So here we have a problem which asks, an object moves along the x-axis such that at any given time t, its position x is given by this position time equation. So x equals 8 plus 12t minus 5t squared. We are asked to sketch graphs of the position, velocity, and acceleration as a function of time for this object. In order to do this problem, I'm going to need the function that they gave me, this position time function, which is 8 plus 12t minus 5t squared. But I'm also going to need, or at least I'll probably need, the functions that describe the velocity and acceleration as a function of time. So I'll need the velocity and acceleration equations as well. And I know that these three quantities are linked by their derivatives. So velocity is the derivative of position, and acceleration is the derivative of velocity. For velocity, I could write this as d dt of x, where x is the function they gave me, 8 plus 12t minus 5t squared. And since since there are three terms to this equation that are being added, I can take the derivative of each piece and just add them up. The derivative of a constant, 8, is 0, and so I can totally get rid of the first term. The derivative of the second term, 12t, is just 12, and the derivative of the last term will be minus 10t. And if you don't remember how to do that, then maybe it would be good to know that in general, for anything that's raised to some exponent, d dt of t to the n would be equal to n times t raised to the power n minus 1. And so when I'm taking the derivative of something that's raised to a certain power, I bring down the exponent and write it as a coefficient. So if the exponent is n, then I would write n as the coefficient in front of the term. And then t remains, and t is then raised to a power n minus 1. So when I took the derivative of 12t, t was raised to a power 1, and so when I subtract 1 from that exponent, I get 0, which is why the derivative of 12t is 12. When I take the derivative of 5t squared, I bring down the exponent, and 5 times 2, the existing coefficient was already 5, so I have to multiply by the coefficient that was brought down. 5 times 2 gives me the 10. T had an exponent of 2, and so when I subtract 1 from that exponent, I just get t to the 1, which we write as t. Next, I can write that the acceleration is d dt of the velocity function, and the velocity function is what I just found. So 12 minus 10t. And I still only need to know that derivative rule that we just talked about. So the derivative of the constant is going to be nothing, it goes away. And the derivative of minus 10t is just minus 10. And so the equation that describes the acceleration is going to be minus 10. The equation that describes the velocity is 12 minus 10t. And the equation that describes the position is 8 plus 12t minus 5t squared. And those three equations alone should allow us to determine what these graphs of position, velocity, and acceleration will look like. I'm going to start with the acceleration graph because I think it's going to be the easiest. So here I'm sketching the axes for the acceleration versus time graph. And what I notice about the acceleration is that in the equation for the acceleration, there's no time dependence. There's not a t in the equation. When I took the derivative of the velocity equation, it went away. And that means the acceleration is constant. It doesn't change with time. And not only do I know that it's constant, but I know the actual value. I know that it's negative 10. And so in my graph, I can write negative 10 as the starting value. And the acceleration at all moments in time is going to be negative 10. So I can just make a horizontal line that is below the time axis for the negative acceleration. The next graph that I'd like to do is the velocity versus time graph. The velocity is going to be a little bit more complicated to graph because the velocity actually does change with time. What I notice about the velocity equation is that it kind of has the form of an equation of a line which looks like y equals mx plus b. I'm going to go ahead and flip the two terms in the velocity equation and instead write the equation as v equals minus 10t plus 12. And hopefully that helps you line up the y equals mx plus b equation a little bit better with the velocity equation, which will make it easier to graph. I know that on the y-axis I'm plotting the velocity, and on the x-axis I'm plotting time, and that's why I've tried to match up those things as I've linearized this equation a little bit. I notice by comparing those two equations that the slope of this graph should be minus 10, which represents the acceleration. And I notice that the y-intercept should be 12, positive 12. And so there should be a positive intercept of plus 12. And the slope of this graph should be minus 10, so the slope should be negative, something like this. And I know it's a straight line because the velocity depends or varies linearly with t. I also know that the velocity is going to be decreasing because of this negative acceleration, and that's given to me by the negative slope, but I can also look specifically at the equation and I can see that there's going to be a certain moment in time where the velocity becomes 0. When negative 10 times t is equal to 12, then the velocity will be equal to 0. And so there's a certain moment in time, and here for this equation happens to be at 1.2 seconds. If you plug in 1.2 for t, you'll get minus 12 plus 12, which gives us a velocity of 0. So I can even add the time where the velocity will become 0. And after that, of course, time can only increase. The velocity will become more and more negative after that, which is why at later times the velocity is down here at some negative value. So despite an initially positive velocity, the velocity becomes 0 and then becomes negative, and that of course is due to that negative acceleration that's acting on this object. The last graph that we'll make is the position versus time graph. And the position versus time graph might be the most complicated because it has the largest dependence on t. It has a term in there that goes as t squared, and so there's going to be a little bit more complex relationship here. The first thing that I would recommend doing to sketch this graph is to look at the position versus time function and plug in 0 time. Plug in t equals 0 and see what you get in the equation in order to at least figure out where to start the graph. And when I plug in t equals 0, both here and here into the position equation, I realize that both of those terms are going to drop out, and the only thing that will remain is the constant, the 8. And 8 is positive, and so my graph needs to start off at positive 8 at t equals 0. From there, I know that the velocity is positive, so the object must be going in the positive direction. And I also know that the velocity is going to be decreasing until it reaches that point of 1.2 seconds. And at that point, the velocity becomes 0, which means the position isn't changing at all, and the slope of that position versus time graph should become 0. So the position is increasing, but the velocity is decreasing. We really need to make sure that we understand that, right? The velocity is decreasing, which means that the slope here should be greater than the slope here. The velocity is decreasing, but the position is increasing. The position is becoming more and more positive because the velocity is positive. If the velocity is positive, the change in position must be in the positive direction. So my graph starts off at 8. It's pointing upwards, but the slope is decreasing. At 1.2 seconds, the slope at this point should be approximately 0 because that's where the object will stop. And as I stated, at moments in time later than that, the velocity becomes negative, and so my position graph should start to slope downwards. It does not mean that the position is negative. The position at this moment in time is still positive because I'm in the first quadrant of the graph, and the position that would correspond on the left-hand side of this graph would still be some positive position. However, the slope now would be directed downwards, which indicates that the velocity would be negative. I think with that, we've got some, well sketched out graphs here. And I want you to notice that x depended on t squared, and we got a curved parabolic graph for the position versus time graph. The velocity depended linearly on t, and we got a straight line for the velocity versus time graph. And the acceleration did not depend on t, and we got a constant flat line for the acceleration versus time graph. Hopefully you can start to see the connections between position, velocity, and acceleration, figuring out how to use the derivatives to find those different functions, and then ultimately using those functions to sketch graphs of position, velocity, and acceleration.